All right, so for today's video lesson, we're going to be talking about the Doppler effect and just what happens when the source that it is producing, either light waves or sound waves, what is going to happen as that object is in motion. So this animation here is showing what occurs at a stationary point source. So this might look familiar if we were to throw a pebble into a calm lake. Okay, we see the wave front kind of spread out equally from the point source. Okay, now if the point source is stationary, we will expect it to kind of radiate out in an equal manner. But if an object is in motion, the wave fronts are going to be affected depending on the type of the motion. Okay, so if an object is moving, so if we have a moving point source, moving slower than the speed of sound, we'll talk about that in a little bit. Okay, but notice that as that object moves from left to right, the wave front to the right of that object is actually being kind of compressed or squished together, and the wave front to the left of that object is further apart. Okay, so if the source is moving towards the observer, they will hear a higher pitch due to a higher frequency. Okay, this is because the sound waves are becoming compressed in between the point source and the ear of the observer. Okay, as that source moves away from an observer, they hear a lower pitch due to a lower frequency, and that is because the waves that are being emitted by the point source have a greater area to kind of spread out. Okay, so as it moves towards an object, those waves will become compressed and we'll hear a higher frequency or a higher pitch. And as it moves away from an observer, you will hear a lower frequency. Okay, this is probably best illustrated or best experienced as we hear a siren from either a fire truck or an ambulance or a police car driving by. Okay, so just in general, the shift in frequencies of a moving point source is called a Doppler shift. So here we have a video of a police siren approaching an observer. So hopefully you're able to hear the increased pitch or the higher frequency of the car, of the emergency vehicle as it was approaching the observer, and as it was driving away from the observer, we experienced a lower frequency or a lower pitch. Again, this is because the just the space in between the source of the sound and the observer is being compressed as it's moving towards the observer, and as it's moving away from the observer, the wavelengths or the frequency is being stretched. Okay, so there are some applications of the Doppler effect. So like sound, light is a wave that can be described in terms of frequency. Okay, so if a star or galaxy is moving away from us, the light it emits will become stretched or redshifted. Okay, again, this is because there's just more space in between the source of the waves and the observer. So there's just more space for those wavelengths to kind of like stretch and become further apart. If a galaxy or star is moving towards us, the light it emits will be compressed or become blue shifted. Okay, so astronomers observed, a lot of the galaxies in the universe that they were able to anyways. And they actually realized that the majority of those observed galaxies are redshifted. So that is going to suggest that the majority of galaxies are moving away from us. And from that overwhelming data set, they came to the conclusion or the hypothesis that our universe is in a state of expansion. Okay, if you're interested about an expanding universe, that is a cosmology course, and you can learn about that in university. And if you're interested about that, come and talk to me, and I can give you some more resources for that. So what happens when we move faster than the speed of sound? Well, what happens is, well, first you need to move really quick. So the speed of sound is about 330 meters per second. So that's like 10 times as fast as driving on the highway. Remember, 120 kilometers per hour. When we convert it to meters per second, it's about 33 meters per second. So the speed of sound is 10 times faster than the speed at which we drive on the highways. Now, it is possible to break the sound barrier, and this has been done before. So the Mach 1 is a jet, which can go really quick. Actually, it can go faster than the speed of sound. So just a couple quotes. So this first one is regarding the speed of sound and shock waves, what happens when you break that sound barrier. So the wave fronts in front of the source are now bunched up at the same point. As a result, an observer in front of the source will detect nothing until the source arrives. The pressure in front will be quite intense, so a shock wave, and this is due to all of the wave fronts adding together. This will be perceived as a pitch, not as a pitch, but as a thump of sound as the pressure wall passes by. So the figure to the right is a bullet traveling at Mach speed. And if you look just to the right of that bullet, you can see the shock wave or the sound wave that is generated by that bullet. Okay, so it's very close to breaking that sound barrier. For jet pilots who fly at Mach 1, so this is the speed of sound, this report that there is a noticeable wall or barrier which must be penetrated before achieving supersonic speeds. So this wall is due to the intense pressure front, and flying within this pressure front produces a very turbulent and bouncy ride. So the bottom right image on your screen is an image of an F-18 jet that can actually break the sound barrier, and that's what it looks like actually. So that white cloud is the jet itself breaking that pressure barrier in front of it. Okay, so supersonic is, this is when something will travel faster than the speed of sound. So when this occurs, a shock wave is occurring when the source exceeds the speed of the sound wave as the wave fronts cross, they interfere. So as this jet or as an object goes faster than the speed of sound, as they cross that barrier that we talked about in the last slide, they will notice this as they break that sound barrier. So a supersonic aircraft usually produces 2 sonic booms. So sonic boom is when we are breaking the sound barrier. So one of those sonic booms will be created from the nose of the aircraft and the other from the tail. This will result in a double thump. Okay, so the figure on the right shows a bullet traveling at 2 times the speed of sound. Okay, so it's just about to break that sound barrier. Okay, so we talked about how different mediums can affect the behavior of waves as they cross mediums. Now, temperature itself is going to affect the speed of sound. So we should know that as things become hotter, the particles are going to move further and further away. Okay, so this will make it easier for the speed of sound or for sound waves to travel through the medium of the air. Okay, so as we increase the temperature here, we'll notice that the velocity of the speed of sound will also increase. Okay, so kind of shifting gears to a little bit of sound and music here. So beats on music. So when two sound waves with different frequencies interfere, they can change the amplitude of that sound wave. Remember, we have constructive interference and deconstructive interference. Okay, so music is actually going to be a collection of sound waves put together, and that is what we hear, and that's music, right? A band or an orchestra, we will have different sounds coming from different instruments, and the collection of all these sound waves is what makes an orchestra very pleasant to listen to. Okay, so for sound quality, our eardrum can only detect a single wave. This wave would be the sum of all the sound waves entering your ear. These waves are in superposition. Remember, these are when waves combine to change their amplitude. Okay, so just in general, the quality of a music note is called the timbre. Okay, we have 6 images here. So number 1, starting at the top left, these are the sound waves produced by striking a tuning fork. So we kind of get a simple sine wave from that. Number 2, we have pure chord, which is produced by a collection of tuning forks being struck together. Okay, so this is where we will experience superposition, right? So the collection of how those sound waves interact with one another. Number 3, so bottom left of your screen, is a beat tone of 2 tuning forks, which almost have the same frequency, okay? And then if we look on the right side, these are going to be some individual instruments. So number 4 is produced by a violin. Number 5 is produced by an oboe. And number 6, bottom right corner of your screen, is produced by a French horn. Okay, so if we detect the frequencies and amplitude as a function of time, it can be kind of difficult for us to understand what is kind of going on. So we have a thing in physics that's called the Fourier transformation. Now, if we switch from a time to a frequency plot, this can allow us to better see the harmonic content. You guys are probably too young for this, but on some of the older stereos, it would actually show like the frequency and the like just in a bar graph right on the front of the stereo. It was a pretty cool touch. Okay, so this is just what the conversion between those 2 graphs looks like. Okay, you don't need to know this, but we can just manipulate our data so it is more presentable for whoever is going to be interpreting that data. Okay, so in our everyday lives, typically the sounds that we hear are due to resonance. So this is the formation of a standing wave. Okay, so in here, this is a violin. So as we are kind of affecting those strings by moving, I don't know what the tool is that he pulls back and forth on the violin, but as he interferes with those waves, depending on the position of his fingers, those chords will produce notes of particular amplitudes. Okay, so here are some common musical notes, and this is just going to show us what the frequency of these notes are and the harmonic of those. Okay, so notice that this 8th harmonic of a pitch will have a frequency of 880. You may wonder how this A on the left side has a frequency of 110 and is the first harmonic. Okay, that is a relationship between the frequency and our harmonics, which you guys don't need to know. Okay, just wanted to show you guys this, just to kind of show you what the frequency of different musical notes are, just for our musically inclined students. Okay, and same thing here. Different notes will give us different frequencies with different harmonics. Okay, so up at the top here, we have like 16 harmonics on that C. Okay, and as we move to the bottom, we'll see that we only have one harmonic in that middle C. For guitars, similar to violins, if you ever play guitar, you'll notice that the positioning of your fingers will influence the sound that is created as you play the guitar. So based on the position of your fingers and how you pluck it, we will also generate different sounds and different frequencies and different notes. All right, so that is it for today's topic, and this is the last topic of Physics 20. So I hope you guys learned lots throughout this semester. And if you have any questions or need help with anything, you know where to find me, okay? Enjoy the rest of your day and have a great Christmas holiday.